All right, in the first half of this section, we talked about how to use, uh, how to construct confidence intervals for a difference in two proportions. Okay, and so we did the last example we did, we estimated that the actual difference in the proportion of U.S. teens versus adults who use social media, we estimated that the true difference is between 0.076 and 0.143. In other words, the difference in the percentage of U.S. teens from U.S. adults that use social media is somewhere between 8 to 14%, roughly. So, what we want to do now is we know that confidence intervals pair nicely with significance tests. So, we want to also talk about how we can do a significance test. And the significance test is trying to find more concretely whether there is truly a difference. And we want to state our hypotheses in terms of are the two proportions the same, would be our null hypothesis, that there's no difference between the two proportions, or alternatively, that there is some difference between the two hypotheses. So let's talk about how we would construct, or excuse me, what conditions need to be met, and how we would prepare for and actually execute a significance test for the difference in two proportions. That's what we're trying to test. Significance testing can be done in the same way as Chapter 9. We will restrict ourselves to only situations, in this course, we'll restrict ourselves to only situations where we consider the null hypothesis to be that there is no difference, right? We call it the no difference statement. We're going to only focus on that type of null hypothesis. So that means all of our hypotheses will be stated like this, right? If there's no difference, then the two proportions would be equal to each other. So our null hypothesis would be simply that P1 equals P2. Another way of saying that is that the difference between the two proportions is 0. These are two different ways of saying the exact same thing. Either one is a perfectly acceptable way of writing your null hypothesis. So let's look at an example here in practice writing our hypotheses. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in two low-income elementary schools. A simple random sample of 80 students from school 1 found that 19 had not eaten breakfast. At school 2, a simple random sample of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. State appropriate hypotheses for a significance test to answer whether these data provide convincing evidence that there is a difference in the population proportions. Don't forget to define any parameters. So again, our null hypothesis, when we run the test, is that there is no difference. So we'd start from the null that P1 and P2 are equal. I think this is probably a more straightforward way for us to think about it, but if you want, you can always write it as P1 minus P2 equals 0. That says the same thing, right? Just basic algebra, subtract P2 from both sides. So you can say either way. Either way is a perfectly good way of saying your null hypothesis. Your alternative hypothesis could be stated two different ways as well. It's just the negation of these things. We're trying to test whether they're equal. The alternative would be that they are not equal. Or you could say, if we're trying to test that the difference is 0, the alternative would be that the difference is not 0. Now, when we get into one-tailed tests, this way of phrasing the hypotheses will be important, because P1 minus P2, if we think that P1 is greater, then we would need to state that this difference is greater than 0. But if we thought P2 is greater, then we would need to say that this difference is less than 0. So we'll talk about that as it comes, but this is how we can state our hypotheses. And of course, we want to make sure we define our parameters here. So let's go ahead and do that. So we can say these are our hypotheses where P1 equals we're trying to test whether the proportion of students who come to school without breakfast is different from one school to the next. So P1 could be the proportion. This is the true proportion of students who go without breakfast at school 1. And then we can say P2 is the true proportion of students who go without breakfast at school 2. Okay, so make sure you always define your hypotheses, always define your parameters when you state your hypotheses. So in this case, we're trying to see whether the true proportions are unequal. Make sure you state what those true proportions P1 and P2 are. Sorry about that long, awkward silence. I thought I had paused it, but I hadn't. Anyhow, let's keep going. So let's talk about the conditions that we would need to check in order to do a significance test for a difference of proportions. They are the same as the conditions for doing a significance test on a single proportion. Exact same conditions. Okay. So that means we need to verify the random sample condition, right? And again, it needs to be true for both samples. We also need to satisfy the 10% condition. Neither of our samples can be greater than 10% of their respective respective populations. So 10% condition has to be true for both samples. And again, for proportions, the large counts needs to be met for both populations, both samples. So that is the number of successes and the number of failures within each sample all need to be greater than 10. Standard deviation formula. We talked about this a little bit in the first half of the section. Let's go back to where we had it. The formula for standard deviation for the difference of proportions, right, is dependent on the true standard deviation, or I should say is dependent on the proportion, the true proportions from the populations, which we might not know. So we use p hat, and that actually gives us the standard error. Okay, we're going to go another step further here with the significance test. When we run the significance test, we're trying to run it based on the hypothesis that both proportions are the same. Well, that's the null hypothesis. If both proportions are the same, then we would expect samples from the two different populations to have the same proportions, same sampling proportions. So we can treat the individual, the two separate populations as one group population, because if they had the same proportion, you could mix them all together and the proportions would all stay the same. So when we go to do to do the standard deviation, right? This is the standard deviation of the statistic. When we go to compute that, we're actually going to pool all the samples together. And that's what this C means. P sub C is if we pool the proportion of successes, and then multiply it by its complement divided by the sample size from the first population. And then the second term is the pooled proportion of successes times the pooled proportion of failures divided by the sample size from the second population. But the key thing to note here is that we're going to pool all of the data from both our samples together, because we're computing this based on the idea that there is no difference. That's the null hypothesis. So that's why we're going to pool successes and failures together in one shot when we do the actual Z statistic. Okay, so just make note of that. When we do it in a problem here, I'll try to emphasize that a little bit more. But again, in order to do the significance test, we have to compute the test statistic, which is always the statistic, that is the sample difference of proportions, minus the parameter, which is the null hypothesis. In this case, we're saying there is no difference. So the sample difference minus the hypothetical difference if they were the same proportions divided by the standard deviation of the difference in proportions. Again, based on pooled proportions, but divided by each separate sample. Okay. So we'll compute some test statistics and see how that goes. So that's just the basic setup for running a significance test. In the next video, we're going to actually execute a significance test to see if there's a difference in two proportions.